First question. In transistor, forward bias is always smaller than the reverse bias. The correct reason is to avoid the excessive heating of transistor, or to maintain a constant base current, or to produce large voltage gain. So if the forward bias is made large, the majority charge carriers would move from emitter to the collector through the base with high velocity. This would give rise to excessive heat, causing damage to the transistor. So forward bias is always made smaller than the reverse bias just to avoid excessive heating of transistor. So correct answer among the given option is option A. Looking towards the next question. In NPN transistor, if doping in base region is increased, then the collector current, will it increases, decreases, remain same, or none of this? So we know that number of holes in base region increases, hence recombination of electron and hole are also increased in this region. As a result, base current increases, which in turn decrease the collector current. So, if doping in base region is increased, then collector current will decrease. So, correct answer among the given option is option B, that it is going to decrease. Next question. When a battery is connected to a P-type semiconductor with a metallic wire, the current in the semiconductor inside the metallic wire and that inside the battery respectively due to. So here we are supposed to find out the specific type of currents present in different parts. So first, the charge carriers inside the P-type semiconductor. So in the P-type semiconductor, we have holes. Then inside the metallic wire, that is inside the conductor, charge carriers are electron. And for the third, we are supposed to look for the battery or for the cell. So for the cell or the battery, we have ions as a charge carriers. So hole, electron and ions respectively. Now look at the option holes. So we have it there, that in two options. Then next is electron. So it's there only in option A, and then ion respectively. So correct answer is option A. Looking towards the next question. Is ionization energy of an isolated free atom different from the ionization energy for the atoms in a crystalline lattice? So ionization energy is basically the amount of energy required to remove the electron from its outermost shell in gas state. Okay, so ionization energy of an isolated atom is different from its value in crystalline lattice or crystalline arrangement of the atom, because in the crystalline lattice, each bounded electron is influenced by many atoms in periodic arrangement of the crystalline lattice. In isolated free atoms, all the electrons are freely available. Okay, so the removal of electron is quite comfortable. While in the case of crystalline lattice, the electrons are in influence of other atoms also, and because of that, the removal of electron will become difficult. So the correct answer among the given option is option A, that it is different from that of each other. Okay, next question. Energy gap of silicon is 1.5 electron volt. So energy value is given in the question. At what wavelength, that means lambda, the silicon will stop to absorb the photon? So here in this question, E is given and we are supposed to find out lambda. So we know a very simple relation that E is equals to Hc upon lambda. We just need to rearrange it, that lambda is equals to Hc upon E. We know that H has a constant value, that is 6.6 into 10 raised to minus 34, and C also have a constant value, that it is 3 into 10 raised to 8. The whole upon energy value which is given in the question, that it is 1.5 electron volt, we'll just substitute it over here. It's 1.5 electron volt, and electron volt need to be converted into the voltage. So we'll put the value, that is 1.6 into 10 raised to minus 19. Now when you do the sum or calculation for this, we get the answer as 8.25 into 10 raised to minus 7 meter. Now we need to convert it into angstrom because all the options are given in terms of angstrom only. Okay, so when you convert this in angstrom, you get 8250 into 10 raised to minus 10 meter, and that is absolutely equals to 8250 angstrom. The photon having wavelength equal to 8250 angstrom or more than this will not be able to overcome the energy gap of silicon. So the correct answer among the given option is option A, that is 8250 angstrom.